Hey everyone, welcome to Cogito Code. From this video, we are starting the Python data structures and algorithm series with the perspective of covering the material which is required for GATE, data science, and artificial intelligence. Okay, so most of the topics and concepts we'll cover will be aligned with the syllabus of GATE DSAI. And I'll be starting with some topics which are like very basics. It may not necessarily be in the syllabus of GATE, but these will be like building blocks for other data structures. So it will be great if we know a little about those, and that will be array and linked list. Okay. So linked list is already in the syllabus, but array isn't. But we'll be learning it anyway because when we'll be learning stack, queues, trees, and all those data structures, it will come handy if we know about arrays. Okay, so let me start with array only. So what is an array? An array is a contagious memory location, not contagious memory location, sorry, a connection of element stored in contagious memory location. So whenever you create an array or a Python list for the people who have done Python and only Python, whenever you create a Python list or an array like this, that 1, 2, 3, 4, this array or these elements has been stored in some memory. Okay, so let's say this is our physical memory here, and these are its building blocks, something like this. This is our physical memory. Now these blocks can be bits, these can be bytes, but let's say we are talking about integers, then we need a block of 4 bytes. If we are storing a float, then that will be different. So we'll simply call these blocks. We won't go into granularity of bits and bytes. So let's say these are our memory blocks. So whenever we declare an array or a list like this, what the system do, it will select a particular portion of memory and store these elements in that. So let's say 1, 2, 3, 4. Okay. So what is very specific about it, that it is a fixed size memory allocation. So you tell your array that I need to store these many elements, and for those many elements, the memory will be allocated. Okay. And it's a single memory location. सिंगल मेमोरी लोकेशन. सो ये सारे के सारे मेमोरी ब्लॉक्स जो हैं वो कंटेजियस हैं, वो साथ में हैं. जस्ट लाइक यू आर गोइंग टू वॉच अ मूवी विथ योर फ्रेंड्स, तो जब तुम साथ में बैठोगे योर सीट्स विल बी इन साइडवेज, राइट. तो सारे लोग साथ में ही बैठे होंगे. सेम वे दिस इज ऑल दीज एलिमेंट्स आर इन सिंगल मेमोरी लोकेशन विथ अ फिक्स साइज मेमोरी. नाउ what is the plus point with it, that you can do random access. So let's say you have created an array and you know this particular memory location, that इस particular point पे हमारा array stored है. So you can simply know that it is stored here, and if I do +1, I'll come to the next element. If I do +1, I'll come to the next element, and so on and so forth. Okay. But let's say now you don't know. So this is very helpful when you already know that kitne elements you need to store. So you can tell beforehand कि ठीक है मुझे 5 elements or 10 elements store करने हैं. So memory give me the storage of 10 elements. But let's say you don't know already how many elements you want to store. So let's say you want to store some 60 elements. Now you didn't know beforehand that it is 60. So if you created an array of less than 60 elements, let's say of 40 elements, then it will throw an error. क्योंकि जो मेमोरी एलोकेट हुई है फॉर योर एरे, इट विल इट विल बी स्पेसिफिक फॉर 40 एलिमेंट्स, उसमें 60 एलिमेंट्स एलोकेट नहीं कर सकते। इट विल थ्रो एन एरर की स्पेस ही नहीं है। और लेट्स से इफ देयर इज लेस एलिमेंट्स, कि 40 एलिमेंट्स के लिए you booked an array and now there is just only 10 elements you stored, then space for 30 elements, so this space जो ऑलरेडी एलोकेट हो चुका है एरे के लिए वो वेस्ट हो जाएगा। दैट इज फ्री मेमोरी, बट वो वेस्टेड पड़ी हुई वहां पे, क्योंकि वहां पे और कुछ स्टोर नहीं हो सकता। So these are some shortcomings of array. What is the benefit? That we can have random access, but shortcomings can that it is very specific when you know that how many elements and what type of elements you want to store. If you store more than specific element, already pre-decided number of element, then it will throw an error कि memory नहीं है। अगर उससे कम elements आप store करोगे तो ठीक है, but वो एक्स्ट्रा मेमोरी आपकी वेस्ट हो जाएगी। सो देन ऑन द कॉन्ट्ररी, क्योंकि ये सारे एलिमेंट साथ में थे एज वी सी, ऑन द कॉन्ट्ररी द linked list comes. So what is linked list do? As the name suggests, linked. ओके, तो यहाँ पे क्या होता है, यहाँ पे हम एक पर्टिकुलर मेमोरी को ब्लॉक नहीं करते। वी डोंट हैव अ कंटेजियस मेमोरी ब्लॉक, we just have a single element block. So let's say we want to store a list 1 2 3 4. What will linked list do? It will take this one and it will allocate the memory somewhere in the memory. Okay, तो somewhere in the memory ये एक हमारा जहां पे भी जगह मिलेगी, जहां पे भी मेमोरी फ्री होगी, वहां पर वन को एलोकेट कर देगा। टू समवेयर एल्स, हमको नहीं पता कहां पे, समवेयर एल्स इन द मेमोरी ये दो एलोकेट हो जाएगा। एंड ये कहां पर है, एट विच मेमोरी, जस्ट अ मोमेंट, या एट विच मेमोरी दिस टू इज एग्जिस्टेड, दैट इज नोन बाय दिस पर्टिकुलर वन एलिमेंट। तो इसके पास होगा एड्रेस ऑफ टू, एंड देन एट सम अनदर मेमोरी लोकेशन जहां पर भी फ्री मेमोरी होगी, थ्री विल बी देयर, एंड इसका जो एड्रेस होगा वो टू के पास होगा, एड्रेस ऑफ थ्री। So linked list is like chain of particular nodes. It is a chain of nodes, and each node has one value, that is this 1 2 3, and one address, that is of next element. Okay, so it's like a scavenger hunt, that if you want to go to, let's say, clue 3, first you have to go to clue 1, you have to decode it, then you will have to go to clue 2, you have to decode it, and then you can go to clue 3. Okay, what is the uh, good side of it? That you don't need to worry about now about a particular memory allocation, क्योंकि अब हम इस तरह से कंटेजियस ब्लॉक को एलोकेट नहीं कर रहे हैं। वी कैन डू दिस लाइक whenever a new element will come, हम कहीं पर भी मेमोरी में जहां पर भी स्पेस होगा वहां पे उसको स्टोर कर देंगे, एंड उसका एड्रेस हम पिछले वाले को डाल देंगे। तो वी डोंट नीड टू वरी अबाउट कि अब हम अगर ज़्यादा एलिमेंट्स स्टोर करेंगे तो हमें एरर आ जाएगा, या फिर अगर हम कम एलिमेंट स्टोर करेंगे तो हमको हमारी मेमोरी वेस्ट हो जाएगी, क्योंकि अब एक टाइम पे सिर्फ एक ही एलिमेंट स्टोर हो रहा है और सिर्फ उसका जो एड्रेस है, नेक्स्ट एलिमेंट का एड्रेस, वो यहाँ पे स्टोर होता है। सो दिस इज द गुड थिंग अबाउट द लिंक्ड लिस्ट, दैट इट हैज दिस चेन ऑफ नोड्स, जिससे कि हमारी मेमोरी में हेल्प हो जाती है। नाउ व्हाट इज द drawback of it that you don't have random access anymore, right? For array, if you know this element, you can simply do +4 and jump into this particular element, right? एक से चार पर जाने के लिए you don't need to worry about this 2 and 3. You can simply do +2 here and you will jump from 1 to 4. You can't do same on linked list. If you want to go to 4, you will come to 1, which is usually called head of the linked list. Then you will go to 2, क्योंकि 1 के पास सिर्फ 2 का एड्रेस है, 2 के पास सिर्फ 3 का एड्रेस है, एंड 3 को ही पता है कि 4 कहाँ पे है. You don't know the memory location of 4 until you go to 3. So you have to do this particular trace from here to here, and then only you can reach. So the problem is with traversal, which we can deal with different strategies. Now there are some different kind of linked list. One is singly linked list. What is singly linked list? That you have these nodes and the address, value and address, and you will be pointing to a different value and address and value and address, and these pointers will be only one-sided like this. Okay, then there comes doubly linked list. So in this, the pointers are on both sides. So here you will have a value, address 1 and address 2. Then this will have value, address 1 and address 2. So address 1 will be again directing to the previous node like this, and same way we can do this. So this is doubly linked list, where we have two-sided arrow that you can go from node 1 to node 2. In singly linked list, we can't come back because node 2 know only the location of node 3, not node 1. But in doubly linked list, node 2 will know the location of node 3 as well as node 1. There's another kind of linked list that is called the circular linked list, in which what happens that same way, let's say this is your value and address, this is your value and address, this is your value and address, and this particular node will have the address of the starting node. So these kind of linked list are called circular linked list, where the last node of the linked list is connected to the first node of the linked list. Okay, so just one simple recall that arrays have random access and which is fast. You don't need to traverse through whole linked list. Let's say there are 1,000 elements. So in array, you can simply take the first element and do +1,000, and you will reach the 1,000th element. But for linked list, you will start from 1, go to 2, then 3, then 4, then 5, and so on till 99 and 1,000. Okay. When do we use it? When our data is already predictable, that how much data we need to store. Okay, and specifically when you want to do read operations quickly, so that we can exploit this random access. Okay, when to use, or what is the pros of linked list? When you don't need random access, obviously if you don't need random access, then it will be fine if you use linked list. Then when data varies, when data size varies, okay, or when frequent insertion or deletion is required. Insertion or deletion is required. We'll see in a bit when we look at the time complexity of these two data structures, that is array and linked list, why that is the case. Okay. So now, before I go to the time complexity, let's take a brief intro. What is time complexity? So for every data structure and every algorithm, we want to see that how good it is doing. And how do we check it? We check it that how the number of operation grows, how the number of operation grows as data size grows. For example, if we need to compare this, so let's say you have the array and you have stored 10 elements in there, and you have a linked list, you also store 10 elements in there. Now you want to predict or get the 10th element. So with the array, you will need to do only one operation. That is, you are at first element or start of the array, and you will do plus 10 in your index, and you will reach at the 10th position. So for array, you will need to do only one operation, right? With linked list, you have to do 10 operations. From first, you will go to second node, then from second, you will go to third node, from third, you will go to fourth node, and so on. Again, if we have grow the data size, let's say now there's 10,000 size of the array and the linked list. There are 10,000 elements in a array and the linked list. Again, for the array, it will be just one operation. You are at the start of the array, you do plus 10,000 at the index, and you will reach the last index, last element, or 10,000 elements. But for linked list, you will have to add like from 1 to 2 to 3 to 4. So now you will need to do 10,000 operations, right? So the time complexity will be worse for linked list than array. So this is the basic definition, that how the number of operation grows as data size grows, and that is the time complexity. Now there are some things about the array and linked list, so I'll write them down, and then we'll compare the time complexities of both. So first thing is, next say access. Okay, access means you need to go into that particular element. I'll write array here, and I'll write linked list here. Okay, one thing is access. Now we have seen this, like access, how do we do in the array? We have taken this previous example where the data size, as the data size is growing, there's no effect on array, it is just one operation. Okay, and but for linked list, as the data size is growing, the number of operations are also growing with linearly with number of elements, right? For 10 elements, the number of operation a linked list will do, that is 10. With 100, 100. With 1000, 1000. So if there is n elements, how many operations we need to do? That is n, right? And usually for the time complexity, there are worst case, best case, and middle case scenarios, but usually we represent this by big O, that is the worst case scenario, because we see that, okay, what is the worst case? So for array, access will be big O of 1. Because even in worst case, even if you want to go to the last element, you will need to do only one operation. What about a linked list? If you want to go till last operation, that will be the worst case, right? That from starting, you need to go to the last with linked list of n elements. So that will take n operation. So that will be big O of n. Okay. Second thing will be search. You have a particular element in mind and you want to search that if that element exists in that array and that linked list. How will you do that? You will check, that is a linear search, that you will go into each particular element and check if that particular element is equal to the element we are searching or not. So let's say this is your array 1 3 5 7 11 9, and same way there is a linked list 1 3 5 7 11 and 9. Okay, and let's say I want to search for 7. How do I search for 7 in the array? I'll go to the first element and check if this is equal to 7. If yes, then well and good. Otherwise, I'll jump to the next and then again and then again. What will be the worst case scenario in that? That the number or the element I'm searching will be on the last index, the last element. So in that case, how many operations, how many lookups I will need to do? That is n, right? If our these particular number of elements are n, then in worst case, I had to do n lookups. What if we are doing the same for linked list? Same thing, right? We'll start from here. We'll check if that is 7. If not, we'll go to the next and next. And worst case scenario, that if this 7 will be here, then we have to go through all till the end, right? So again, n operations. So search will be big of n for array and big of n for linked list. Now there's some ways we can reduce this big of n, that is like binary search and all other things which we'll learn later. What next? Next is let's say insertion. You want to add an element. Okay, so what will be the insertion of array? It depends. So let's say you want to add some element and remove these things. And write insertion at beginning and insertion at end. And we can do in middle also, right? Insertion at mid. Okay, so let's say this is your array 1 2 3 4. Okay, and this is your linked list 1 2 3 4. Okay, mind that this is a contiguous block of memory, right? So all of this is like this. Now if you want to insert something in beginning, okay, and there's other elements like these are free memory, free blocks. Let's say it has like 10 blocks allocated and only 4 is filled, 1 2 3 4. Now you want to store something at beginning. How do you do that? You can't simply add something here. There's no space, there's no memory. What you will need to do, you need to shift these elements. So this 4 need to come here, this 4 will need to come here, this 3 will need to come here, this 2 will need to come here, so that this particular memory can be free. If this memory block is free, then only you can insert something in at beginning, right? So how many operations you will need to do if you want to store something at the beginning of an array? You will need to shift all those elements. So let's say there are n elements, then you will need to shift n elements to its right, so that your first memory block can be free and you can put your new element at the beginning. How many operations are those? N operations, right? So insertion at beginning will be big of n. What about linked list? What about linked list? Do we need to shift these? No, right? Because they are not contiguous. These are at some random place, at some random place of memory. Okay. What we need to do, this thing has this particular one's address. If we want to add something new here, what we'll do, we'll create a new node. We'll have, let's say, 5 here, and we'll put this one's address at its address list, right? So simply the new linked list will be that we have created this new node 5 and we put one's address here and we simply added it. We didn't want to do anything with these elements. These are like this only. 2, 3, 4, right? We didn't do anything with these elements. So no matter what the size of list is, we simply added a new node at the beginning, which is at some random location of the memory. How many operations that is? That is just one operation, right? This linked list could have 10 elements, could have 100 elements, could have 1,000 elements. We didn't care. We just added this one here. So how many operations that is? That is one operation. So insertion at beginning will be big of 1. What about insertion and AND? Same way, I'll remove all this. Okay, so this is your initial array and this is your initial linked list. Now you want to add something at the end. And again, remember the block analogy in the case of array. So this is your memory block and this is where this 1, 2, 3, 4 is allocated. So you want something to add here. How do you do this? You just come here. You know that you were here. You just come here doing one operation, right? You have random access. You can go to this particular location with just one operation and you add something here, right? No matter what the size of the array, it could have 10, it could have 100 elements, it could have 10,000 elements. You need to do just one operation to go to the last and add one element. That is just one operation, no matter what the size of array is, right? So insertion at AND will be take big of 1. What about linked list? If you want to add something here, you will start from here and you need to reach here. So you have to start from here, jump here, then jump here, then jump here. And when you reach the end, then only you will be able to add something here. So let's say if you have 10 elements in your linked list, how many jumps you will need to do? 10. If you have 100, how many jumps? 100. And if you have 10,000 elements, how many jumps you will need to do to reach the end? That will be 10,000 jumps. So as you can see, if you have n elements, it will need n jumps or n operations to reach the end and add a new element. So the time complexity, the worst case time complexity of this will be big of n. What about the middle part? In middle part, both of these are big of n. Why so? Because in array, if you want to add something at this particular location, you need to shift these. And if you want to add something here in the linked list, you need to hop these. So in both cases, you have to do n number of operations if that n is before the that mid part where you want to store the new element. In array, you have to shift, and in next list, you have to hop, right? So what will be the worst case of mid? That you will go to end for this next list, right? That you need to shift on the, you need to hop on the n elements. And what will be the worst case of for array? That you need to shift all the elements. So that is the beginning, that you have to insert something at beginning. So like worst of both, big O of n and big O of n. Okay, and remove all this. What is the next thing after insertion? That is deletion. Again, deletion at beginning, deletion at end, and in the middle. So beginning, and the middle. So again, let's say you want to delete something at beginning of an array. This is your array, 1, 2, 3, 4, and again the same block analogy, 1, 2, 3, 4. These are your memory blocks, and you want to something delete from this particular. Let's say you want to delete 1. So you remove this from here. Now this can't be this way, right? This first element should be starting from here. So you will need to shift all these elements to left. You deleted first element. Now you will need to shift this 2 here, this 3 here, and 4 here. And the last memory block will be empty. Cannot be the case that first is empty and then others are full. So how many operations you need to do? If there are 10 elements, you will need to shift 10 elements, or 9 because you deleted 1. If you have 1000, then you have to do 999. If you have 10,000, then you need to shift 9,999. So that is almost like n operations, right? You have to shift n minus 1 elements to your left if you delete something from the beginning. So that will be big O of n. What about in the case of linked list? You should have guessed it by now that this is 1, this is 2, this is 3, this is 4. You want to delete this. Okay, let's say this, there is a head pointer which has the location of this particular element, the address or location of this particular element. What you'll do, you can simply say, okay, this is not anymore head. I'll go here, and now this is the head, and you remove this. Your first element is removed. You still have your whole linked list, and you didn't do any operation on them. This could have been 10 element long or 10,000 element long. Doesn't matter. You just beheaded it. You just remove the first element, and the whole chain, you didn't do any operation. So that will be just big of one operation, right? No matter how long the linked list is, you just need to do one operation to remove the first one. What about deleting the end? Again, you should tell it by now that this is your particular array, and you need to remove this 4. What you do, you need to just do one operation to get it to the 4 and just remove it, right? From here, you will do just one operation to reach this particular element because you have random access in the arrays, and then you delete it. So that will be just big of 1. What about the linked list? Again, you need to remove the 4, and you have the address of 1 only. What you do, you start from 1, go to 2, then 3, and then you remove the 4. So again, if the list is 10,000 elements now, you have to do 10,000 hops or 10,000 operation to go to the last node and then remove it. So that will be big of an operations. Although it could be better if you, when you create a linked list, you take a 10 pointer or end pointer, but that is like a different choice. But in general, that is big of. What about deletion at middle? Again, the worst of both. That in particular uh, this case, you will again need to shift some elements. If you delete something here, you will need to shift those elements. And if you want to delete something here, then you need to hop these elements. So the worst case for array will be when you delete the first element, and the worst case for linked list will be when you delete the last element. So again, the worst of both. So deletion in the mid will be big of n, and for this also big of n. Okay. What about a little space complexity? So what is space complexity? That how much memory is allocated for the storage. Okay. Space complexity. Okay. So if you store n elements in an array, what will be the storage of that? That will be big of n, right? Because you have stored n element in consecutive blocks, and that n blocks has been occupied by your array. What about linked list? Should it be big of 1? No, right? It will be also big of n, because even though the memory blocks are not contagious, they are in different or some random memory locations, but still they are taking space, right? So if you have n elements, they will be taking n blocks, not contagious but some random memory location, but they will be taking n blocks. So that is also big of n. Is there some memory overhead? Memory overhead is when you store something extra than the values itself. Okay. So in the array, you don't require any extra addresses or elements to store, right? So memory overhead for array is none. You only store the elements. What about a linked list? Linked list store addresses, right? Or the pointers to the next node, right? So first node will have the element and also the pointer for the next node. Second node will have the element but also the pointer for the third node. So this memory overhead linked list do have. Okay, addresses or pointers. What about dynamic sizing? So as you can see that array has fixed size. It has no dynamic resizing. If you full the array, you have full the array, and now you cannot add any more elements. If you have less than the required element, then your memory is wasted. Okay. What about linked list? It has dynamic size. You can add more and more and more elements, and even you can shrink it, right? It won't cost you extra space. That okay, these space is allocated but is not in use. Okay. What about efficiency? So the we have seen that at what type of work linked list is better, and at what kind of work the arrays are better. But what about Python list? So you may have seen Python list, and you'll be wondering that Python list, is it a linked list or an array? Because you don't need to already specify the number of elements in Python, right? You can just add so many elements there. So you can just do this dot append operation, and you can add as many elements as you need. So at first point, you may think that it is a linked list because name also resemble like list, linked list, and also it is also dynamic, but that is not the case. Under the hood, Python list is an dynamic array. How does that work? So initially Python from itself, you do not need to specify the data type, you don't need to specify the number of elements. Python by itself give you an array of a particular size. Let's say size n. Okay, so by itself Python will allocate some memory in the memory, allocate some space in the memory and give it to you. Now as you will be filling it, and when Python will see that okay, this size is not sufficient, this is about to full, okay, this is about to fill full, then what the Python will do, it will create a new array bigger than this. Let's say this is size n, then it will create a array of size 2n, copy all these particular elements in the new array, and now you have a bigger array. It is an array, but a dynamic array which Python is managing itself. And whenever you try to fill this up, you can keep doing the append operation and you'll keep filling it up. And again, when Python will see, okay, that this array size is not sufficient, it will create a new array, a bigger one, copy these particular elements in the new one, and give the rest of the space to for you to use. Okay, so this was a quick intro in the concept of array, linked list, and a brief about how the Python list work under the hood. We'll be coming with more videos on stack and queues and trees. So these were bare basics. Oh yes, Ashwin, do you have a doubt?
Yeah, I had a few doubts. One is that is there any constraint on the type of data which these particular data structures can hold?
So you need to define in languages like Java or C++, you need to already define the data type, because for each data type, let's say if you are using an integer, the memory size each integer will take, that will be 4 bytes. So let's say you want to store 10 integers, then the compiler need to allocate the memory of 40 bytes. But if you want to store a long, that is 8 byte. So then the compiler for the same 10 elements, you have the compiler need to allocate the memory of 80 bytes. So for languages like Java and C++, you need to already specify the data type. But in the case of Python, because Python manages it all internally, then you need not to define. One more thing, in languages like Java or Python, you can only store one, not Python, Java or C++, you can only store one type of data structure or data type in an array. So it can be either an array of integers or an array of nongs or an array of floats. But what Python do, Python give you this flexibility that in the same list, you can have an array, you can have an integer, you can have a float, you can have a string all together.
What about linked lists? Can it store elements of the same type or different types also?
Same. So for linked list, again, the different languages gives you different kind of flexibilities. In Python, we don't have a concept of linked list because we have best of both worlds, the list data structure itself. But in other language, for list also you need to define the particular data type.
Okay. And we also talked about doubly linked list, right? So I had one doubt there also ki, why suppose single way we are only pointing to the upcoming node, the next node which is
Yeah.
there. Doubly may we point back also.
Yes.
So if we have this functionality to point back, तो हम
Yeah.
सिंगल लिंक लिस्ट यूज ही क्यों कर रहे हैं? एंड इफ मेमोरी ओवरहेड इज द प्रॉब्लम, देन कितना सीरियस इम्प्लीकेशन है उसका? How much extra does it actually take for single to become doubly?
Yeah, so it's about the use case, right? So if your use case is fulfilled with the single linked list only, that there's not much problem that you need to traverse like this, and we'll see the use cases of single linked list and double linked list when we uh, study the much more like next upcoming data structures. So it's about the use case. If your use case is fulfilled with the single linked list, why we take another these addresses and uh, you do the memory overhead, right? So, and these linked lists can be really long. So let's say this is 1 million elements are there, then you don't need that, okay, there's one extra element at each of your node.
So does it take some extra time or space, or what exactly happens in terms of that experiment?
Extra space. So for even for this particular element, you will need to specify some memory, right? So let's say your particular, you are storing integers. So let's say this is your 4-byte integer, and this is one pointer which is like 1 byte, right? Now let's say there are 1 million elements. So if you need to store one more pointer, then there will be 1 million bytes extra. But if your use case allows that, then you can have that overhead that, okay, it is necessary for me, then I'll have this arrow as well. But if it is not needed, then 1 million byte, why will you want to spend 1 million byte of space?
Okay, so basically we have some extra space complexity in terms of doubly linked list, but the time complexity is the same, correct?
Yes. Yeah.
Okay. One more doubt I had is that in terms of array, we talked about three things: insertion, deletion.
Yep.
The three types of insertions and deletions which were there, right?
Yeah.
So my doubt here is that we talked कि अगर हमको beginning में डालना है, it was we said कि we shift the array.
Yeah.
या फिर in the end we add it in the end itself, or in the middle also we have to shift the right part.
Yeah.
Same goes for deletion, the whatever counterparts were there. My issue here is अगर हमने let's say 10 elements का एक array बनाया है and वो memory block 10 का ही था, तो how does this shifting work in a static array? Dynamic में ठीक है, you explained कि वो double हो जाता है and everything happens systematically in Python. But let's say
you're talking about addition or deletion?
Both. I mean, addition may it will be an extra space कि अगर space constrained है तो how extra space will happen. Deletion में तो ठीक है, I understand कि it will just shift and that extra space will go away.
Insertion will only happen if there is extra space, right? If there is no extra space, if all of your memory blocks is full, then the insertion cannot happen. But let's say you created an array of 10 elements and you have only 5 there. Okay, you already have allocated the space for 10 elements, and then you have allocated or added 5 elements in the array. Now you can do these operations that you can add at the end or add at the beginning or in the middle, but that is only possible if the memory is available. If that is not the case, then this insertion will not happen.
So let's assume that it starts from, just for the sake of this example, let's say the memory location starts from 15.
Okay.
Okay, so we have 15, 16, 17, 18, and 19. For this particular example, it was occupied. And now we have to add something at the beginning. So
Okay.
will it be added in the 14th one, or will it be added at 15 and everything else will be shifted?
So you're saying that, okay, this is our array like this, and it has some empty space. And this is your particular...
At the back also and at the front also. Let's say there's some empty space.
So in array, there is no space in the front. What happens when you create an array? Whenever you create an array, this particular node's address. So because you are doing this consecutive elements, let's say four of friend went to a movie, right? So let's say this is your friend A, this is your friend B, this is your friend C, and this is your friend D. And you need to call your friend E and tell it that, okay, where you are seated in the which row or which seat. What will you do? You will give this A seat number and say, okay, we are there only. So that when the E will come, he will search for this A, and then he will know that, okay, you are just there. So same happen in array. Whenever you create an array, this particular element that is 15, its address will be given to you. If you code in C, then the particular, whenever you are you create an array, the pointer for the first element is given. So these things are omitted in the languages like Python, but in Python also this particular elements as address is given. So there is no space in the front. Now if you want to add something in the front, what you need to, you will need to shift all this, that 18, 17, 16, 15, that 15, 16, 17, 18 will go here, and 14 will come here. Then only this thing will be on the front because the address is given of this particular block only.
Okay, got it.
Okay. Same happen for deletion. If you delete this one, you can't access this particular array element. So you need to shift this at 15.
And let's say the seat was not available afterwards. Like let's say one more friend had come, but there were only 4 seats. Then it'll throw an error, right?
It will throw an error. Correct. Because you have booked that particular like 4 seats or 5 seats in your memory or in your movie theater. You can't have just randomly come people and sit.
And how does that, for example, if we have to define the size beforehand, right? Let's say 10 elements. So
Yeah.
how does then that work exactly? If we add one more element, how does that size change from 10 to 11 dynamically without us defining it?
Sorry, can you come again?
Let's say we are defining an array and we specify that it should have 10 elements.
Okay.
So when we add one more element, that particular specification we did has changed. So how does that happen?
No. That won't happen. So if you have decided already that there will be an array of 10 elements, you can't add more than 10 elements. So
Okay, so the insertion and deletion case, so basically the insertion case was for a dynamic array.
not the dynamic, you can do it in also. Let's say you have created an array of 10 elements and now you have only 6 elements there, that 5, 6, 7, 8, 9. Now there are 4 empty blocks which are there.
Okay,
So
got it.
what you can do, you can add things in the front and shift these in the back. You can add in the back, you can add in the middle and shift these two ahead. Just like in movie theater, if you book the seat for 10 persons, only 10 person can shift. Now if new persons are coming, new people are coming, you can either make them sit in the front, but then again all of them need to shift, or in the middle, then the left ones need not to shift but right one will need to shift, or in the end then no one will need to shift, but only those seats which you have already allocated.
Yeah, got it. Those were all of the doubts that I had. Thank you.
Okay, so guys, this was our student representative, and we have recently started a discourse channel. You can join that discourse channel for the doubts you are facing in these concepts. If you have any doubt in the particular video, or in general in ML concept, AI concept, or in gate preparation, you can ask them there. And if you want, you can also come in these live sessions when we are recording it, and you can ask your doubts right here, right now, when we are particularly doing these recordings. So you can join our Discord channel. The link for that or the QR for that should be visible in the front of your screen now. So do join our Discord channel, subscribe, give it a like, comment what you need to see or which topics you need us to cover, and we'll be coming up with more topics on DSA and AI and machine learning for the GATE DA syllabus. Thank you.